Yeah, I'm ready. Thank you for the introduction. So, as it was mentioned, my name is Victor Vad, and I will talk about robust cone step mapping. In this work, our research interest was mesogeometry rendering. While macrogeometry is usually in the scale of tens of pixels or a group of pixels, and the microgeometry is a sub-pixel resolution data, and it's usually modeled as a BRDF or such. We call mesogeometry those geometric details which are usually in the realm of pixels. And of course, there are many modern and state-of-the-art methods to render high complexity geometries, such as the non-hypothetic games. These techniques work on high resolution meshes, which has a very high memory footprint. Also, these techniques include complex processing, pre-processing, and runtime filtering, which makes it very difficult and non-trivial to integrate into an existing rendering system. So our approach is that we render a simple geometry. For the simplicity, we used a two-triangle quad, and we apply a texture to it as usually, very classically. But also, this is what we get, but we also include a height map, and we render it in a way that we say that there is a virtual box that from a ray which shot from a pixel hits on the top, which is basically the quad. And there is a virtual button which can be set dynamically, and we use a ray casting method and find the intersection of the surface defined by the height map. So it's a very classical method. And despite it's not brand new, it has some advantages. So for example, it has a very low memory footprint, and also it basically needs the pixel shader to be modified, so it makes it easy to integrate into any existing system. And if someone was in the game industry, such myself, knows that, for example, during crunch time, it's a very important property. Also, it easily allows dynamic height maps in theory. However, there are some problems. For example, it only allows explicit surfaces, so there are no holes or cavities in this setup. And as we investigated, it turned out that it's difficult to implement it in a robust and efficient way. In practice, this height map rendering is usually done in a direct per pixel displacement map. So basically, during ray casting, a simple linear search is done, and maybe one or two refinement steps. In this case, it was a second refinement step is done. And yes, we can say that the result is quite okay. It looks nice. But this rendering used 200 iteration steps, which is quite high even nowadays, especially if we have a frame budget, like 60 seconds. So in practice, they usually use a much lower iteration number, and then we can see that many artifacts will appear. So in the literature, they try to use some fastering methods. So for example, Dahmer introduced cone step mapping. The idea is that alongside the height, each texel stores an angle of a cone. This cone is, the apex of the cone is on the surface, and the angle is pre-computed in a way that basically we choose the maximal unbounding cone. So in this way, the ray can skip a significant empty space. So how does it work? This is our virtual box. The top is the quad that we are rendering. We compute the two intersection points on the top and the bottom, entry and exit points. And we sample the position. We compute the cone. And then we descend the sampling position until the intersection of the ray and the cone. And then we do it again. There is a new cone there, and so on, and so on, and so on, and so on, until we find the intersection of the surface is reached. This is a very nice method, and we were wondering why it is that it was not that much, at least according to our experiences, it's not widespread. But we have some educated guesses. So for example, the generation of the cone map is extremely complex and takes some time. So two authors, Walasek and Ban, quite recently introduced the quick cone map generation on the GPU. And this has much lower complexity. And despite the resulting cones have a lower aperture, the cones are still unbounding. And why am I always saying that unbounding and reaches? That's because Policarpo and Oliveira introduced relaxed cone step mapping, which means that the cones relaxed in the sense that the descending, that this is the conservative ray, and the relaxed cone, basically, the descending ray can intersect the surface in a way that the most once, so the ray can hit the surface most once before hitting the cone. But there are problems with these techniques. So, for example, cones tends to be smaller close to a surface, and the solution for that was originally in the previously mentioned papers that there was a global minimum trace parameter. So when they realized that the next step is too small, they simply use this global minimum parameter as a step size. But our observation is that there's no global constant which can work in every scenario. So whatever we set as a parameter, there will be always holes and surface feature that will be missed. So our first contribution is that instead of one fixed parameter, let's use an adaptive correction. The technique is also might be quite familiar from other scenarios, but what we use is that we computed the distance to the next cell. So in this way, we ensure that we do not skip any important surface details. So in this way, we already modified the rendering algorithm. But there are other problems. Usually, the cones are sampled with bilinear filtering, as usually in graphics. So for example, there is one cone here, one cone in another pixel, but when we are sampling between them, what we see is that the resulting cone will not be unbounding. In some cases, this is not a problem. For example, in the blue area, which is also not part of the proper surface. But in these cases, refinement can find the intersection properly. But there are other cases when we cannot recover from here, so some surface feature will be missed. For this problem, we are proposing another technique, a cross-process step. This is our second contribution. In this step, we have the result of the cone generation. Either it is relaxed or conservative. And then, in every 3x3, for each pixel, for every 3x3 neighborhood, we choose the minimum and simply set it there. So let's check that what these two contributions already produced. There is I hope it can be seen. So there is a test scene, which is like 512 times 500 tiles. It's basically a black background, meaning that most of the pixels are on the ground of the virtual box, except there are some white dots, like a discrete direct delta or something, in a regular grid. So let's see how these techniques can reconstruct this feature. On the left side, you can see a kind of ground truth. We computed it with 10,000 step size of linear search. And the constant mapping and the relaxed constant mapping have problems to reconstruct these fine detailed features. On the other hand, if we use simple constant mapping but with overstep and bilinear correction, as mentioned before, then it already could reconstruct this really high detailed feature as well. Around a decade ago, Badod, sorry if I'm murdering his name, so he observed that the relaxed cone map, which was, so the relaxed cone map has some issues. So the relaxed cone map uses an approximation to generate these cone maps, and it has problems to capture the surface properly. It can skip significant surface hit points, and this is even more likely when the raycasting, the ray sampling is already below the top of the virtual box. This is because they approximated the cones from the top of the box. And also, since it was a brute force approximation, the original generation algorithm was really slow. So to remedy this, we have, I think, the biggest contribution in this work. We introduced the exact relaxed cone mapping. It means that, in theory, the idea is that we compute limiting point. So, for example, this is the continuous height surface. We assume that this is differentiable at the moment. And we consider this limiting point, and these limiting points are those points where the directional derivative is negative. And for a specific point, we take these limiting points of this point of interest, and we choose that minimal one, which is not connected to the point of interest, and we take the minimal cone angle for that, and this will be the exact relaxed cone. For comparison, an incorrect relaxed cone would look something like this. Of course, it depends on some approximation parameters. However, in practice, we don't have we have bilinear patches between textiles, which are not differentiable everywhere. So in practice, we use the simple technique. So for example, this is the point of interest that we would like to compute the cone. And what we do is that we go through these bilinear patches. So the search is done in these 2x2 textile frames. And from the footprint of these bilinear patches, the 4 height values, we can easily compute if there is an existence of a limiting point. To compute the exact limiting point, we would need equation to solve, but we didn't do that. We simply said that, okay, let's find the corner of the bilinear patch, which is closest to the point of interest, so that for that point we computed the cone angle. So let's compare some results, and we use really high iteration and refinement steps to show what our algorithms and the previous one can do. So the first test case, I think everyone knows this texture. And if we render it with a relaxed constant map, we would say that, yeah, this is quite nice. But if we see some details, we saw some missed surface features. And if we use our exact real cone map and overstep and bilinear corrections, we can see that these details are not missed anymore. So again, this is the previous relaxed cone step map, and this is our corrections and exact cone map. And these are some zoomed versions of these details. Another example is a little bit more practical one. And again, the iteration and refinement steps are the same. And what we see here with the relaxed cone map, well, it also looks nice at the first glance, but we can, on the top left side, we see some floating objects, and it will be visible if we see our correction and cone map generation technique. So again, this was the relaxed, this was the cone step map, and if we zoom in, we can see the difference quite well. And also, this is the EGSR logo, left relaxed cone step map, and right with our corrections and cone generation. Well, since we achieved this robustness in a way that we narrowed the angles, so it means that the raycasting cannot skip that much empty spaces, we assumed that, okay, the rendering time will be higher, so the technique will be slower as the relaxed cone step map. So we had to measure the performance. For that, we used the AMD 5700 GPU. I would like to point out that this is not a state-of-the-art GPU, but as far as I know, this is something similar than the PS5s can have. We used a height map of resolution 512, and the output resolution was in full HD. Root refinement was 7 binary search steps, and if we compare the result, we can see that the original trace and the overstep corrected trace was used for all scenarios, and also sometimes we use the bilinear fix or we didn't. And what we see is that yes, the approximated relaxed cone step maps are the fastest ones still, but on the other hand, our method can produce roughly the same speed as the original cone steps map, meanwhile being robust, and meanwhile not skipping surface details. Here we use 32 iterations, which are roughly the one that in practice can be used. But if we are using 200 iterations, then basically the numbers show the same. The original approximated relaxed cone step map are the faster, but our method is comparable to the original cone step map. So as a conclusion, so we identified robustness issues in the representation and the rendering algorithm, and we proposed solutions, and we made the conservative and the relaxed cone step mapping techniques a robust rendering method. So these are robust. We can now render depth, distance maps and height maps quite robust way. The first contribution was that we have modified the rendering algorithm, so small surface features are not skipped. The second contribution was that we have compensated the effect of bilinear filtering with the pre-filter step. And the third contribution was that we proposed a novel that we called exact relaxed cone map generation method. And the rendering speed is still remained comparable with the original and the relaxed step mapping method. In our future work, one of the most important one, that clean cone map generation, a quick cone map generation for the exact relaxed cone maps, something similar that our two authors did with the unbounding cone maps. Also, we would like to apply animated height maps. And most important, and one of the important things that we are really interested in using height fields on realistic curved surfaces. And basically, that concludes my talk, so thank you for your attention.